Hi, my name is Jesse Burkhart. I'm an assistant professor in the Department of Agricultural and Resource Economics at Colorado State University, and this talk is about how clean are electric vehicles. So the topics I was asked to talk about for this were basically how are EVs powered, coal energy versus renewables, where's the energy coming from, and who's producing the energy. I kind of boiled this down into one main question, and that question is how clean are electric vehicles? So today, to answer this question, I'm going to review one paper in economics on this topic. It's a paper by Stephen Holland and a couple of other authors. It was published in 2016, so it's a little bit old, but I think the findings are still relevant. The paper is titled, "Are There Environmental Benefits from Driving Electric Vehicles? The Importance of Local Factors," and it was published in the American Economic Review. So how clean are electric vehicles? What are the considerations that this paper is looking into? First, they're going to talk about global pollutants or greenhouse gases, pollutants that travel all around the globe. And then they're going to talk about local pollutants. And they're primarily going to focus on local pollution, the damages from local pollution from driving gasoline and electric vehicles. And local pollutants are pollutants that don't travel necessarily around the entire globe, like PM2.5, PM10, ozone, SO2, and VOCs, volatile organic compounds. The local pollutants act differently for gasoline and electric vehicles, and it's for the following reason. So gasoline is burned at the location the car is driven, and so the local pollutants are essentially localized to where the gasoline car is driven. On the other hand, an electric vehicle doesn't produce any local pollutants when it's driven, but instead it's producing those local pollutants when you're charging it. And the pollutants might be generated up to 500 miles away where that electricity is generated. So this is displacing local damages from electric vehicles. And the extent of local emissions damages depends on where the cars are driven. Are they driven in urban areas or rural areas? Who's being exposed? If you drive a gasoline car in an urban area, you're exposing many more people than you would be if you're driving that same car in a rural area. And this means also that pollution is often exported across political jurisdictions, especially for electric vehicles. So if you're a state policymaker trying to decide what's your optimal subsidy for electric vehicles, do you consider the damages from local pollutants from EVs in your state, or do you consider the damages outside the state as well? So these two figures kind of give an example of the effect of driving gasoline-powered vehicles versus electric vehicles on local pollutants. So these are the simulated changes in PM2.5 from an additional 10,000 Ford Focuses in Fulton County, Georgia, where we're thinking about gas-powered vehicles on the left and electric vehicles on the right. And you can see for the gas-powered map, this Fulton County is bright or dark red here. And this basically says that most of the local pollutants from driving 10,000 additional gas-powered vehicles are concentrated right there in Fulton County. There's some leakage, that's the green, but not nearly as much as what you see in the electric, for the electric vehicles on the right. And you can see that Fulton County is not even really highlighted in the graph to the right for the electric vehicles. In fact, most of the power is generated in North Carolina. You can see that the local damages are occurring up in North Carolina, primarily in the orange, the sort of orange spot there. But a lot of the power is still coming from elsewhere in the country, even some parts of the Midwest, and so you can see that there's still additional local damages all the way up into Michigan. So the electric vehicles are displacing their local damages quite a bit more than the gasoline-powered vehicles. The bottom line policy result is that the optimal electric vehicle subsidy should be equal to the difference in lifetime damages between an electric vehicle and a gasoline-powered vehicle. In other words, people should be indifferent between purchasing the gas-powered vehicle and the electric vehicle, given the subsidy. And this paper asks, what are those lifetime damages and how do they differ by region of the U.S.? So we're going to consider the global, the greenhouse gas damages, and the local damages. The results in the paper up front: if we're only accounting for greenhouse gases, electric vehicles are environmentally superior almost everywhere across the U.S. So this means if we ignore the local pollutant damages, electric vehicles are environmentally superior to gas-powered vehicles. So then what happens if we account for the local pollutant damages? If accounting for local pollutants, the optimal national subsidy is negative $1,095, or actually a tax. In California, but this is different depending on where you're driving the electric vehicle, and it differs based on the grid, the electricity grid. So, for example, in California with clean energy, relatively clean energy, and high local pollutant damages, there's large population centers, so you're exposing a lot of people when you drive a gas-powered vehicle. Then the optimal subsidy is actually $2,785, so it's positive. This is the subsidy for an electric vehicle. In North Dakota, on the other hand, where we have relatively dirty energy, maybe coal and natural gas, and low local pollutant damages, we're in a rural area where we're not really exposing many people if we drive a gas-powered car. The optimal subsidy is actually negative $4,964, or roughly a $5,000 tax. Also, 91% of local pollutant damages from electric vehicles are exported across state lines, just like we saw in the previous slide. And in contrast, only 19% of local pollutant damages from gas-powered vehicles are exported across state lines. And not accounting for these exports, the best electric vehicle subsidy is positive in 32 states. But if you account for these exports of local pollutant damages, then the best electric vehicle subsidy is positive in only 11 states. So these two maps show county-level local and global emissions damages from gasoline-powered vehicles and electric vehicles on the left and right, respectively. You can see that the damages from gasoline-powered vehicles are highest in urban areas like San Francisco, LA, San Diego, Chicago, New York, the major urban areas. And then the damages from electric vehicles are uniform in these big regions. Like the western U.S. is all the same color green. The upper Midwest, all the way to Pennsylvania, is all the same color dark red, and that's because these are interconnected regions for electricity grids. And so what the right-hand map is basically saying is that if you charge an electric vehicle anywhere in the West, the marginal electricity production for that electric vehicle is coming from the same place. And so you're going to get the same emissions damages regardless of where you charge that car in the West, or likewise in the upper Midwest and where the damages are highest. If you charge an electric car anywhere up in the upper Midwest all the way to Pennsylvania, those marginal damages are coming from the same place, the same generator, and so that's all a uniform color. These two maps show the optimal state-level electric vehicle subsidy accounting for pollution spillovers on the left. So if we account for the damages that are spilled over to other states, then we see that there's a lot of negative subsidies, negative optimal subsidies. In other words, there's a lot of places where the optimal subsidy is a tax, particularly up in the Midwest and then on the East Coast and even in the South. And that's because those electricity grids are relatively dirty, especially compared with the West. On the bottom right, we have the optimal state level electric vehicle subsidies if we don't account for pollution spillovers. So if we don't account for the local damages that are being displaced to other states. And in this case, we have a lot more positive subsidies. So it depends on whether or not you want to think about the damages that you're inflicting on people not within your political jurisdiction. Some qualifications of this study. So we need to think about the types of vehicles being considered. are we comparing a Ford F-150 to a Chevy Volt, or are we comparing a Ford Focus to a Chevy Volt? Now, this paper compares a Ford Focus to a Chevy Volt, but if we could get people to substitute a Chevy Volt for an F-150, then these maps would look a lot different. This paper also uses the social cost of carbon of $41 per ton. Current estimates are well above $50 per ton, so if we update that, then these maps would probably look a little different as well. The analysis is based on an electricity grid from 2010 to 2012. Clearly, the grid has developed since then. We have more renewables, and so the grid's going to look a little cleaner, so maybe these subsidies are going to look a little more positive in some places. It depends on when the EV is charged. This paper assumes that the customers are charging at night. In some cases, it's cleaner to charge your electricity maybe during the peak hours. So if we had coordinated electric vehicle charging, we could do better. And it considers a marginal electric vehicle with few EVs on the road. With more electric vehicles, the grid will expand and these estimates will differ. So some conclusions: if only considering global emissions, electric vehicles look better than gas-powered vehicles. We already said that. But if we consider local emissions, we've seen there's lots of variation depending on how electricity is produced and whether the vehicles are driven in population centers. In other words, who's exposed. Electric vehicles look better as electricity production becomes cleaner and we can coordinate charging times with periods of lower electricity emissions. This analysis ignores the possibility of long-term benefits from today's investments. For example, technological innovation like grid expansion or better batteries, these things are a public good and therefore they're underprovided, and subsidies help with this. This paper ignores that, and so if we consider those, then maybe the subsidies would look a little better as well. So thank you, and I hopefully can take some questions.